Boolean algebra is more of an optional subject. You're not going to find this mentioned in most workplaces. Boolean algebra, it's very interesting, and you can see the application to the ladder logic diagrams as you do this lab. It makes you more acutely aware of and, or, nor, and De Morgan's theorem about flipping the type of instruction and flipping the and to an or and vice versa, and it creates a complement. And this will actually help you write your code. So we had you do the lab, and it was really straightforward. And I think the only thing you might have trouble wrapping your head around maybe is how you're going to apply this. Now, taken a little bit further, Boolean algebra can be used. You can actually write out an algebraic expression of logic and then simplify it so you end up with a rung with less instructions in it. I typically don't do that because I like to write code in a way that's the easiest to read by the people that have to read it out on the shop floor in a hurry. I don't want to end up with something that's really elegant and clever and tricky and takes less instructions. I would rather use more instructions and make it bang, 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 readable, readable, readable. So let's go ahead and discuss this lab project. George Boole was a largely self-taught English mathematician, philosopher, and logician, most of whose short career was spent as the first professor of mathematics at Queen's College, Cork, in Ireland. He worked in the fields of differential equations and algebraic logic, and is best known as the author of the Laws of Thought, which contains Boolean algebra. Remember that 1815 to 1864, there was no thought of computers yet. There were mechanical machines considered, so the thought process was in the works. Boolean logic is credited with laying the foundations for the information age. Boole himself maintained that no general method for the solution of questions in the theory of probabilities can be established which does not explicitly recognize not only the special numerical basis of the science, but also those universal laws of thought which are the basis of all reasoning, and which, whatever they may be as to their essence, are at least mathematical as to their form. And I'm quoting George Boole on that. I suppose I could have converted that to 2020-21 English. If you're more interested in George Boole and his book, The Laws of Thought, go to Amazon and read it. In a nutshell, Boole declared that all decisions can be reduced to yes or no, true or false, on or off. Now, I paraphrase with the on or off, but never would you reduce them to the values of 1 or 0. 1 or 0 we do use in computers to store the state of a bit. It's a 1 or a 0, it's on or it's off. But the logical decisions are reduced to yes or no, true or false, on or off. A good example is, let's say that you decide you're hungry. Well, you may not have consciously asked the questions, am I hungry? And then that was a yes or a no. But you're hungry, yes. Is there anything to eat? Yes or no. Go to the pantry. Is there anything in here that appeals to me? Yes or no. Do I need to go to a restaurant to get something that appeals to me? Yes or no. So all decisions can be broken down to a myriad of simpler conclusions. And that's typically what we do when we write logic for PLCs, PACs. The AND law. Let's start with that one. Now remember, this is not an exhaustive presentation of Boolean algebra because we're not actually going to do any calculations. We're only showing you examples of the laws of Boolean algebra. And you can use Boolean algebra to simplify your logic. In the beginning, or I should say back in the day, I used Boolean algebra because memory was very expensive and I had to reduce the logic to the least number of expressions or instructions and memory location use that I could possibly get away with just to conserve memory. Memory is no longer expensive, and I seldom ever hear of anyone running out of memory in a PLC or a PAC, at least a modern one. The AND law. So we look at the truth table, and in the left-hand columns, it shows the logical state of A and the logical state of B. That's not A and B, that's just a column of A and a column of B. In the right-hand column, that represents the logical state of A and B together. So let's take the first one. If you have a false and a false, well, that ends up a false. If you have a false and a true, in other words, you have a statement and part of it is false and the other part is true, well, it's false. The statement's false. Same thing if by distribution A is true and B is false, the result of A and B is false. If A and B are both true, then A and B is true. So in other words, if A is true and B is true, then A and B together as a conclusion is true. So we take one rung of logic, input 0, input 1, and output 0. And we label them A and B. These two instructions are both true if on. So if A is on and B is on, then the rung is true. If A is on and B is on, then the rung is false, because the second rung says if A is on and B is off, then output 1, true 1. But if they're both on, then the rung is false. So an A and not B gives you a true. At the top again, if A is on and B is on, then the rung is true. The second rung, if A is on and B is off, then the rung is true. The third rung, if A is off and B is on, then the rung is true. And the last choice would be if both A and B are off, then the rung is true. For two conditions ANDed together, there are four possibilities. That is, when I say possibilities, I mean logical, not memory state. That's another matter, and we're going to get to that. So we have four individual rungs here. Every one of them is a unique logical statement. A and B, A and not B, not A and B, not A and not B. Four completely separate statements. Now, let's take that same logic. Now, I'll back up here so you can look at these four. A and B, A and not B, not A and B, not A and not B. Is this or is this not the exact same logic? Now what we're looking at is the state of the bits in memory that are being read by those two instructions. The first one says if A is on and B is on, of course neither one is on. How do you know? Because of the blue text. It tells you the state of the bit. But notice here half of the instructions are blue, but all of the bits in memory are blue. That is because half of these instructions are true if off. And if the bits are off, then half of them are true and half of them are false. That's simple. A is off and B is off. Take the next case where A is on and B is off. And notice the same rung is not true. And answer this question to yourself. Are both of these four rungs identical logically? Look at the one on the left. A and B, A and not B, not A and B, not A and not B. Go over to the next one on the right. Says the same thing. A and B, A and not B, not A and B, not A and not B. But because of the state of the memory locations, the same rungs are not true or false between these two. So in other words, these four rungs of logic, and we'll say these are in your PLC, when the state of the input changes, then the logical state of the rungs also change. So what we're doing here is making sure that you don't confuse true and false with on and off. Two completely different things, because when you compare the second instruction in both of the top two rungs, A and B, A and not B. So B and not B are not the same thing, and B cannot be on and off simultaneously. But true and false is not the same as on and off. Let's do a third one. In this one, we basically flip around the second one. We have A off and B on. Notice that in the four rungs now, you have three different comparisons of the states of A and B, whether they're on or off in memory. All three of them yield a different result. So we're using the exact same logic in all three, but getting three different results. Same thinking, three different results. Do a fourth one, and again, all four of these are the same four rungs of logic. Logically, they read and state the exact same thing. If A and B, then output 0. If A and not B, then output 1. If not A and B, then output 2. If not A and not B, then output 3. So notice that In the first one, 3 is on. In the second, 1 is on. Then 2 is on. And then 0 is on. 4 different results from the same 4 rungs of logic. The OR law, let's look at the truth table. If I back up and look at the truth table for the AND, I'll just back this up real quick. Notice that the A and B, the right-hand column, and that's an asterisk, that's multiplication. So one thing we didn't do is, I didn't say, if I multiply A and B together, false times false is false, false times true is false, true times false is false, and true times true is true. If you converted this to ones and zeros, 0 times 0 is 0. 0 times 1 is 0. 1 times 0 is 0. 1 times 1 is 1. Now we're not using zeros and ones. So let me jump forward here again to the OR law and look at this truth table. Where the AND truth table, the result was false, 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 true. And remember that the state of A and the state of B in the left-hand columns are the exact same pattern. So instead of getting false, 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 true, you get just the opposite. You get false, true, true, true. Now, looking at this rung of logic, you're looking at it and, well, it's obvious to you. Either input 0 or input 1 can turn on output 4. Comparing, just your basic knowledge of electricity. And by the way, that's why if you don't have a decent grasp of current flow and conductance and resistance and a complete circuit with conditions and loads, you're going to struggle with ladder logic diagrams. So if you're taking this course and you're looking at these symbols of 2 parallel vertical bars with an empty space and you don't know what that means, then you better back up and watch basic electricity magnetism and some of the other lectures and then come back to Boolean algebra. We're just assuming that you electrically are squared away with a complete path for current flow through either A or B. Now, ORing is adding. So if we take the left 2 columns, the column A and the column B, and we make those ones or zeros, 0 plus 0 is 0. 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is 2, except there is no 2 in Boolean algebra. That's why it's best to stick to true and false. So if we have an OR situation, and if one of 2 things is true, then you're going to do something. A and B, both false, then it's false. So false plus false is false. 0 plus 0 is 0. Now here's a second rung, but the first one says if A is on or B is on, then output 4. The second one says if A is on or B is off, then output 5. The third one says if A is off or B is on, then output 6. And the last one says if A is off and B is off, then output 7. Now the fact that we have 4 possible on-off combinations for 2 bits and the fact that we have 4 rungs is irrelevant. The rungs are true or false. The bits are on or off. So let's take the first situation where A is off and B is off. And you can see it's exactly the opposite as it was for the AND. With the AND, if they were both off, then the last one was true. In this case, the first one, well, the last one was true. In this case, they're all true but the first one, where A or B, neither one is on, so true if on A, false. True if on B, false. So a false plus a false is a false. And you can go right on down. Now, remind yourself, this logic is identical to what we saw on the previous page. These 4 rungs right here are these 4 rungs. And in this instance, we're saying both input 0 and input 1 are off. Now let's take the next one where input A is on and input B is off. But the logic is still the same. Those 4 rungs are identical between the first example and the second. But the results are not, because the states of A and B are not the same in both cases. So 4 rungs, each with 2 bits of memory being examined, and the logic is different in each rung, ends up giving you many possibilities for results. Let's take the third one, where A is off and B is on. And really there's not much difference between the second one and the third one. We just kind of flip which is on and which is off. And then the last one, of course, is both on. So with both on, the first rung, A or B, they're both on, so it's true. A or not B. The first one, the true if on, it's true. In the third rung, true if off A, it's false. True if on B, it's true. In the last rung, true if off A, it's on, therefore it's false. True if off B, it's on, therefore it's false. De Morgan's theorem, August De Morgan, also a contemporary of George Boole, born a little earlier, died a little later. London, England, English mathematician and logician, basically the same as Boole, whose major contributions to the study of logic, which is what we're dealing with, include the formulation of De Morgan's laws and work leading to the development of the theory of relations. We're talking about relations between pieces of data and the rise of modern symbolic or mathematical logic. Neither one of these gentlemen had anything to do with electronics, and if you know anything about Boolean algebra, it's used predominantly for logic gates, for solid state logic. You may or may not have an experience with it. My first experience was with the 7400 chipset, quad AND gates, quad OR gates, quad NOR gates, etc. And if you were designing a circuit, which I did, I used both Boolean algebra and De Morgan's theorem to reduce the total number of gates. Yeah, my last name is Gates. Nothing to do with the logic though. De Morgan's theorem. His theorem states that complementing the result of ORing variables together is equivalent to ANDing the complements of the individual variables. So in other words, if you flip the ORing and you flip to the complements of the individual variables, you're going to end up with some equivalency. Also, complementing the result of ANDing variables together is equivalent to ORing the complements of the individual variables. And you're thinking, well, this is a bunch of gobbledygook. Well, let's look at some examples. Okay, here's the first one. And this is right from the ones that we just showed you. Now remember, in the lab manual, we didn't use A and B. We just used inputs and outputs. Why repeat what you did in the manual? What we're doing here is really the same thing, but we used A and B and true for the names on the bits of memory. So look at the first one. And remember, if we back up here, it says equivalent to ANDing the complements or equivalent to ORing the complements of the individual variables. So in the first rung, you've got true if off A and true if off B. So the complements of those two instructions would be true if on A and true if on B. So what we did was we ORed what was ANDed in the first rung and then used the complements. We took true if A and made it true if on. We took true B, true if off, and made it B, true if on. So we took the complements of those two instructions and we ORed it instead of ANDed it. And what we end up with is a complement. In other words, the second rung is the exact complement to the first rung. So if you're looking for the opposite for the first rung, that's the second rung. Here's another one. Now I'm going to use all four rungs from the logic that we've been looking at. So you can see that just like in the first one, we took the complement of the first rung, true if off A and true if off B. Okay, and in the second rung, we made it true if on A or true if on B. Now go down to the second pair, the bottom, true if on A and true if off B. So we took the true if on A, made it true if off A. We took the true if off B and made it true if on B, and we ORed it instead of ANDed it, and we end up with a complement. And I'm doing this for all four rungs. Here's the third one, where the second one on the previous, the second one down there, notice A is on and B is off, right? Look at the red and the blue text. So when it comes to the text on the instruction, that's the on-off state of the bit in memory. I know you know that, just reminding you. Okay, so we flip that around, and now we have A on and B off. But the logic is true if A is on, true if B is off. So we take and we flip the true if on A to true if off A, and the true if off B to true if on B, and we OR it instead of AND it, and we ended up with the exact opposite state, the complement. And the last one, of course, is if A and B are both on, then true. And the second one, if A or B are both off, then true. Now I want you to look at these pairs of rungs and think about it. Let's just take this last one. If A and B are both on, then the output's on. That means if either one of them is off, then it's going to be false, right? I mean, just in looking at that, we'll say the third rung on the slide here. If A is on and if B is on, then the rung is true. Therefore, if either one of them is off, then the rung's false. It's just straight up logic. Now, with only 2 bits in play, this is not much of a paradox. And De Morgan was the master of paradoxes. And basically, a paradox is something where a solution is seemingly illogical. Okay. Exclusive OR. Here's an exclusive OR logic. This is not De Morgan's theorem. This is just an exclusive OR. So an OR is if A or B. An exclusive OR is if A and not B, or not A and B. It is exclusively if A or B, but not if both A and B, like the last rung was in a couple slides ago, where if all of them were true except for the one where neither one was on. So go down through here and look at your choices. Only 2 of them are true. The second rung, if A and not B, because look at the red and blue text. The red text, IN00, the blue text, IN01. So the upper half of that rung, the upper branch is true, and you go right down below it, the upper branch is false, and the lower branch is true. You go down the last one, neither branch is true, just like the first rung. Neither branch is true. Exclusive OR. So this was just a brief canvassing or summary or presentation on Boolean algebra, the examples, not actually doing calculations with Boolean algebra. It's hard for me to say how much my use of this, not just these examples, but actually using Boolean algebraic expressions to solve logic down to the fewest number of instructions and memory locations. It's hard to say how much that enhanced my understanding of logic as I moved from solid state gates in the 7400 series of integrated circuits and on through into relay logic and then now into PLC, PAC logic. Okay, I squeezed about as much out of that as I thought I could that was appropriate for your learning path. You might say that we strayed off the reservation a little bit, or our straight line learning path concept that we use for designing our learning path, that would be just on the edge. It enhances your ability to understand the logic in terms of proper formal terms like and or and nor, and De Morgan's theorem of creating a complement of logic by flipping the instruction from direct to reverse and then flipping it from and to or to and. So really your takeaway should just be kind of a more interesting understanding of basic ladder logic. Thank you.